Thank you everyone for joining us for the Microsoft Research Summit today. Hopefully you have gained insights into some of the ways that Microsoft researchers and academic collaborators are thinking about the next generation of efficient deep learning models. We are approaching AI from different perspectives, which include not only creating more powerful models, but also developing unique ways to create AI techniques that are innovative, fair, and responsible while being mindful of emerging opportunities and risks. It's my pleasure to present the last session of this track, where we will enjoy a fireside chat hosted by Susan Dumais, Technical Fellow and Lab Director here at MSR. Susan will be joined by Microsoft's Chief Scientific Officer, Eric Horvitz, and Professor Yi-Jin Choi of the University of Washington. Together, they will look ahead at the next generation of AI systems, the most important lines of research, and how we can turn research into technologies that bring the benefits of AI to more people more often.
Hello, everyone. My name is Susan Dumais. I'm a technical fellow at Microsoft and the director of our research labs in Cambridge, Massachusetts, New York City, and Montreal. I'd like to welcome you to the final session of the Efficient Large-Scale AI track at Microsoft's Research Summit. In this session, I'll be hosting a fireside chat with two luminaries in the field of AI, Yi-Jin Choi and Eric Horvitz. Yi-Jin is a professor of computer science at the University of Washington and also a research manager at AI2. She's very well known for her work in natural language processing, spanning language understanding, language generation, and common sense reasoning. Eric is a technical fellow and chief scientific officer at Microsoft. He's well known for his research at the intersection of machine learning, reasoning, and decision-making, and for integrating these research insights into new human AI experiences and applications, especially in healthcare and information management. So during this track on efficient large-scale AI, you've heard about recent advances, starting with a keynote about where we are now and what we need to do to continue to develop AI that empowers more people more of the time. Following the keynote, there were 3 research sessions that looked at efficient training and inference, that looked at robustness and generalization, and human AI collaboration. And in this fireside chat, we'll wrap up by considering what's next in large-scale AI. And I've restricted the discussion here to 2 very large and general themes. The first is scale and robustness, or lack thereof, in today's AI systems, and the impacts of AI on people and society. So let me just start with a few reflections and then get to lots of insights and input from our fireside chat speakers. So many advances that we've seen in the last 5 years come from using semi-supervised training methods, typically with transformer architectures, using more training data, developing larger models with literally billions of parameters. And so Yi-Jin and Eric, do you think that progress in AI is going to continue to come from bigger and bigger models with more and more data? Or have we plateaued, and will other innovations be needed? So Yi-Jin, let me start with you. I know you've done a lot of work on structure, learning from demonstration, and so on. Would love to hear whether we will continue to go bigger and bigger, or we will need to develop new techniques.
Yeah, that's a great question. I personally believe that we will be surprised yet another time and then another time by how much the scale can improve the performance further up. And people do say that things are plateauing, but the truth is that then people also find out how to compress the models. There's recent very exciting results that compresses 16-bit models down to 8-bit model, for example, that allows for scaling things up even further. And then as far as the data plateauing, it depends. These days, we also do data augmentation or automatic generation of the data in order to address that concern. So I do think that larger models will be able to demonstrate more powerful results. Having said that, I do think that there's something inefficient about the way that current AI systems work. So if we have another paradigm shift such that it can learn concepts in a way that humans learn, more data efficient learning may be possible. But even so, I do think that scale is likely to be a necessary condition for powerful AI models. Not sufficient, but nonetheless necessary condition for making things work well.
Eric, any thoughts on this?
Well, I've been very intrigued by the magic and emergence we've seen in scale. And I expect more. I agree with you, Ajit. I think we're going to be surprised by what we see with scale, but also with the richness and diversity of the data types that we're training on. In core principles with scale, the bigger is better. It has been justified by some interesting recent work by Sebastian Bubeck and collaborators showing the theoretical power of larger models for generalization, and that might not be going away so soon. But I think there are many other challenges and directions that are not solely based on size. New forms of decomposition and modularity that lets us flexibly adapt sets of models to applications that can be wired together. I see new approaches to fine-tuning, including working on specific manipulations of specific layers in neural architectures. This idea of using synthetic data, even generated data about mathematical concepts or structural relationships are showing signs of being able to extend the prior capabilities of these platform models to make them faster at being fine-tuned with less amounts of data. And then on this area of robustness and generalization, last year at the Research Summit, I moderated a session with Joshua Bengio and Yuta Pearl and Susan Athey on causality and causal machine learning. And just in the last 12 months, we're seeing really interesting work on learning about to learn causal effects or to leverage causal effects in showing invariance and addressing issues, for example, of confounding variables, like, for example, handling the challenge with common backgrounds, commonly linked backgrounds to objects, like seeing land behind water birds, for example, leading to misclassifications. Causal modeling sort of helping us to remove these confounding variables, leading to systems that could do better with shifts in distribution, which is, of course, so common in real world applications, going from the laboratory into the open world.
Yeah, I was actually just going to talk about shifts in distribution. A lot of the models really assume that the world is static and that observations are IID. And so the notion of causal models is a really interesting one in which one can more efficiently learn from data to pull out the relevant signals. But are there other algorithmic breakthroughs or new evaluations that you think will be needed to really model and effectively and efficiently adapt to constantly changing environments? You can't knock a model in the head and start from scratch every time there are new experiences. So how do we handle not just distributional shifts, but continual learning? So Eric, do you want to take this one?
Yeah, I've been really intrigued with methods. They seem so natural and organic, the way we as humans learn per natural intelligence. But what are prospects for doing more of this continual lifelong learning? It's an important dimension of intelligence. And I think will be very important in robustness and generalization. Especially important in moving from laboratory-based, as you mentioned, Susan, static metrics and benchmarks into the open world, where we can have to assume out of distribution challenges and new distinctions and needs coming up. Thinking about even for personalization, that is, how do you custom tailor, let's say, a model that might be off the shelf or pre-trained for a population with an individual's patterns of activity and preferences and needs, which are necessarily revealed over time. I have to say that on this critical area of personalization for capturing the nuances of what we want and how, how we speak, and for computers to learn along with a person that a computer is supporting, we're just putting final touches this week on a camera-ready paper on work led by Dan Bohus and Sean Andrus on continual learning to recognize objects by a computer in a kitchen scenario where the system is helping a human being work, and the various objects, it's an egocentric HoloLens point of view, objects and viewpoints are always shifting, and there's motion blur, and the human being is referring to objects with all sorts of natural language snippets, and the system is learning over time to become better as a kitchen recognizer and assistant. And we found that even the metrics that are available today for tracking competencies over time and for talking about what is the competency with continual learning are challenging to work with. We have to come up with new ideas for even benchmarking our systems.
Yeah, thanks. So, Jen, I know you thought a lot about benchmarks and in particular how one might need different kinds of benchmarks for things like dialogue systems. And if one's learning in a world constantly, it feels like we need to break away from the very popular and important sort of static benchmarks as we know them. Do you have any thoughts on what kinds of methods we can use to constantly evolve our measurement of new AI systems?
Yeah, that's a great question. I mean, I did generate a lot of benchmarks, but I don't feel like I generated benchmarks to measure all aspects of intelligence at all. I only feel like I scratched the surface so far. And by that analogy, I do not believe that there's going to be one magic benchmark that is going to be the proof of AI progress on its own. There's no such a thing. Even if it's a benchmark that's interactive, even if it's a benchmark that involves deployment in the wild, I still do not think that it's going to be able to test all aspects of important intelligence, of the progress of intelligence. So the way that I think about benchmarks is that unlike in the past when somebody generates a benchmark and then for a decade it's still there, the shelf life used to be forever. Now we entered this new era where people are barely catching up with the advancements of AI performances, AI models performing well on the benchmarks and being able to especially catching on, relying on spurious patterns in the benchmarks so that they pretend to do well just by sort of memorizing the patterns of the benchmarks without actually learning the underlying concept. So I do think that we do, as a community, this is the biggest challenge that we are having with the benchmarking, which really challenges us to think more creatively to come up with benchmarks that can really test the underlying conceptual understanding. And, earlier discussion had something to do with the causal reasoning. And we're not concerned with very accurate mathematical causal reasoning here. We also need to be concerned about more day-to-day casual causal reasoning that people do, such as common sense reasoning. And even that turns out to be all around difficult things to measure reliably. And part of the challenge is that, especially if we want to evaluate generative models that generates machine output, we currently don't really have reliable evaluation metrics. If it's based on predefined equations, it doesn't necessarily align with what humans consider as proper evaluation. And then if it's model-based, then, well, the model itself doesn't really understand correct versus incorrect output all that reliably. So all around this requires a lot more research going forward.
Yeah, I think I have a love-hate relationships with with benchmarks. I've for many years now, more than 30, been on the NIST's TREC committee. But I still, as you say, there are many real world challenges that are inherent in these kind of challenges and difficulties that are inherent in these static collections. We don't even know what space of competencies these benchmarks typically sample.
Well, on the left
And
side,
so
Susan, I know that you're well known as a benchmark and evaluation guru in this community and IR and beyond.
Well, I think of myself as an evaluation guru and a metrics wonk, but benchmarks are only one aspect of that. There are many, many other ways. And I'm sure, Ye-Jin, when you and your team worked on the Alexa challenge, you had a whole new set of capabilities to think about how systems were performing. It wasn't just static benchmarks, but watching them interact with people in real time and watching people's evolution of interaction patterns in real time. So I think you've both highlighted that there are lots of opportunities to better understand and make sense of the feedback signals that we're getting in many different ways. So, Ye-Jin, I want to go back to something that that you mentioned. We've talked a lot about how open world deployment of systems leads to unforeseen circumstances, and current AI systems often fail really miserably in these cases. You mentioned common sense reasoning. Is it something that you think can help in situations that require going beyond prescribed rules or learned associations? I mean, you've described common sense as the dark matter of AI, something that shapes almost everything we do and need to do, but really challenging to operationalize. So what are your thoughts on the role of common sense in some of these situations?
Yeah, absolutely. I do think common sense will be among the, I don't know, most important, I'm biased toward it, but most important challenges that we're going to be solving over the next decade or so. Like you said, I do believe that common sense is dark matter. Dark matter is 95% of the universe, controlling, influencing what we do observe in the remainder 5%. Without dark matter, what we observe does not make sense because dark matter is bending the trajectory of light, for example. And so common sense is influencing the way that people reason, people use language, people understand language, or people interpret images and so forth. So it's always there. But the current leaderboards and, when you look at these things, it looks as if you can get away without having a strong common sense model. And I do think it's because in the leaderboard setting, there's always a training and test distribution that is identical. So you can memorize a lot of those patterns and then get away with it. But like you said, in the real world deployment, there's unforeseen situations. And in real world, rare events are not rare anymore. And that's where we really need to have the real conceptual understanding of how the world works, which is common sense knowledge. And I do think that really solving it requires thinking things really differently from how things are working right now based on just a lot of raw data and then memorizing what word, trying to predict which word comes next. And that's not proper understanding of language. I do hope and believe that we're going to figure out how to teach concepts more in a principled way to machines.
Yeah. So, Eric, I know you've long sought to understand the human mind. What role, if any, does common sense or other capabilities play in that? And what are some of the big opportunities there?
Well, it's always been shocking to people outside of AI how hard common sense is. It's been a long-term result in AI that the incredible efficient access people have to knowledge about space and time, about intentions, about causation, the results of actions, notions of ethical behavior and norms that we all live with are not even mentioned in dictionaries. It's kind of I love the dark matter term that Ye-Jin was using earlier, and to even put our eyes on it and our attention towards it has taken attempts which failed dramatically to build systems that can operate in the open world and be like people. So I think it's going to be this direction is going to be really critical for, we mentioned earlier, for robustness and generalization, understanding the invariants that we all deal with as humans, that machines see as fluents when they look at the world. Understanding the results of actions, mitigations, the what ifs we live with, and we imagine for our imagination and our plans, what we call counterfactual reasoning. This will be critical. I mean, common sense is the critical underlying fabric. I really enjoyed some of the work that Yejin's team has done, and Yejin has led with Martin Sapp and others on teaching systems using deep neural models explicitly what will happen following actions, or this is, the atomic system, to celebrate you, Yejin, and your team, or the human intentions, the event to mind work. How do we figure out what people want, what people will think if something happens to them or with them. But I think that some directions that I'm really hungry to see further work on is taking our current fabrics and our approaches to reasoning and learning and coupling them with simulations that provide qualitative or even more detailed models of what happens, the mechanics and dynamics of the world, the coupling of logical and probabilistic inference with these large-scale deep neural networks. I think it's another direction for introducing notions of causality and what if into our systems to give them some reasoning abilities that might align more with what we call common sense.
Yeah, no, those are really great reflections, to both of you. One follow-up question, most models today learn from examples. But I know, Yejin, you've looked at how people and machines can learn from demonstration or from language itself. I mean, language itself is a very abstract, higher level, and really important communication mechanism amongst people. Do you see some of the methods that we're using to, quote, train the systems evolving to take into account things like demonstration, language as explicit instructions, simulation, and so on?
Oh, yeah, absolutely. In some sense, the way that we teach common sense knowledge in our previous work known as Atomic at Comet that Eric mentioned, is a form of teaching machines by declarative knowledge as opposed to input-output examples. In that these are not the input-output of some QA problems that we want to solve, but rather it's directly the knowledge that you're trying to teach to machines that you are articulating in the way that, in some sense, caregivers do to their children. Children do ask a lot of why questions and simple questions that require answers that are declarative by nature. And it's the kind of knowledge that we don't speak out among adults, but we do speak such knowledge out for children while they're acquiring knowledge. So I do think a part of it we can address through more definitional, declarative knowledge. Part of it, we could do that through instructions. And recent results based on, for example, my colleagues, Hannah Harji-Sharji, as well as former colleague Daniel Khashabi and many other co-authors, try to test the ability of teaching models through instructions. In the way, similarly, GPT-3 instruct would have been trained. And the results is very, very promising in that when models are trained deliberately with natural language instructions, it's more likely that they're going to understand instructions for an entirely new task, even without demonstration examples. So I think we just need to go more into that direction. And I do think that that's a step toward being able to teach machines more interactively. The real interaction is hard to do at scale because there are a lot of potential issues that can arise when you deploy a system for training purposes that's not even fully trained or anything, and actually interact with the people. So there can be hazard. But that is how human intelligence, I think, is fundamentally different from machines in that we really interact with the world and then we learn. So that gap might be one of the many reasons as to why current AI is both amazing. I mean, in two different ways: amazing for doing really amazing things, but also making amazing mistakes.
Yeah, actually, let me use that to shift gears a little bit in what we're talking about. So, we've talked so far about how we can improve AI models, but I think we also need to ensure that we understand and anticipate effects that these models will have on people and society, and that we deliver meaningful improvements to the way that people interact in their worlds and with each other. And so I think one important step in that direction is something that you were just leading to, which is the ability to align models with human intents and goals. And so, AI systems for the most part are designed to predict some outcome, whether it's the next word or code snippet to generate, medical treatment to recommend, what search results to show. But there's much less thought given to the decisions and actions that people make on these outputs. I think there are just big opportunities and challenges in engaging with people as active participants in the direction and use of AI models that I think you were alluding to. Eric, I know you've thought a ton about human-machine complementarity, and indeed have created models that learn to blend algorithmic and human capabilities in real time. Can you talk about some of the potential of this for blending algorithmic AI with some of the people's values grounded in the real world?
Yeah, we often think about AI as automation, and of course there'll be lots of interesting automation that will come our way over the next several decades. But one of the biggest impacts and influences that AI technologies will have in the world will be on how they work with human beings, with people, and enhance our lives, help extend our capabilities, and so on. And it's a fabulously rich area for thinking through, and quite complex. It's human beings in the open world make the open world even more complicated than the world without humans. So one direction is understanding signals from people. So, for example, understanding what they're good at, and what they can use some help doing, and ideal, sort of in a complementary way, what machines at any point in development that we've come to can do poorly and well. If we give signals about what people are good at and not so good at to our machine learning procedures or algorithms, we can build systems that understand where to put their machine learning effort and their discrimination into places where people might need their help, and add a layer of control or mixed initiative on top of that to understand when machines might want to come forward to help, or come forward to ask people to tap them on the shoulder and say, I need help with this in the task that you've assigned to me. The idea of doing joint optimization of these kinds of goals with the human goals in mind on a task at focus of attention, I think it's a really interesting and rich direction. Another direction is giving people the ability to shape the way models work. For example, if we're concerned about models, large-scale neural models that might be generating output that's toxic or unfair, inappropriate, the notion of having whole systems that involve humans and that can be guided by people to teach machines the nuances of language. For example, that it's okay to talk about minorities with neutral cases. Don't filter them out just because I'm linking some tagged toxic data to be linked with, for example, any mention of a minority group. There's some subtleties, and humans can guide, and like our auto-test work, available on GitHub now, is an example of that kind of work, of a human shaping the behavior of large-scale neural models. But a big opportunity more generally is to think deeply about how can AI systems learn to lean in and ask questions of humans of things they don't understand to learn more. This idea of a dynamic value of information computation to guide, to give systems curiosity about things they might need to understand better with human input or other kinds of signals. Another big area I just want to mention is getting utility functions, okay, costs and benefits of what people care about into our AI system. So it's not just about prediction or classification, but action in the world and thinking deeply about the meaningful nature of the action in the world. What's the outcome going to be like? Is it good or bad? What does the person I'm trying to, or the task I'm working on, what's valued? And I think we've done so little of that kind of embedding real world utility theoretic representations and considerations into our machine learning systems these days. It's a huge opportunity area.
But that means we have to, potentially learn new models, or at least adapt existing foundational models to individuals, to tasks, to this constant, really coevolution of people's practices and the model's competencies. And that seems really challenging, Agent. Again, I'm going to ask you to reflect on this, with regard to how models and people can best co-evolve and learn from each other.
Yeah, that's a really great question. And this, I also want to make this book recommendation. I really loved Brian Christian, The Alignment Problem. Basically, quick summary is that...
You have that handy with you for this?
No, actually I didn't, but it's in my bookshelf. And because Eric was going first, then I remembered, I could use this book. Yeah, so it's easy for humans to talk to each other to align other human behavior, even for this recording, I can align myself a little bit to the middle and things like that. But that is possible only because we do understand a great deal about the social norms and how the world works and so forth. And then if machines don't know that well enough, then, when we put just like reinforcement learning where they can get feedback, machines always come up with some degenerate solutions that nobody thought about. And it turns out humans, even scientists, don't necessarily know what we want in terms of clean, well-defined equations or, criteria, utility functions. So I do think that part of the challenge is that we cannot assume that there can be a data set specific or task specific mechanism in which we can really truly teach machines what do we know just by demonstration or by utility function. I don't think either of them will be truly meaningful. And probably we do need to worry about the underlying shared values that humans have and try to teach that to machines. And I think what Eric meant by, different utility functions, especially in terms of cost benefits, really go into that direction where we do really need to understand what people do care. And then also answering Sue's question about different individuals having potentially different value system. It's not the case that people are entirely at odds, but we do understand that for certain political topics, I might have some understanding about how other people may or may not agree with me, or for certain kinds of social norms, I might, even if it's not political, I might understand that there can be some differences. Do you wear shoes in your house or not, for example? So I think we can...
Not allowed in my house.
I'm okay either way, surprisingly, but not back in Korea where I'm from. So it's important, I think, for us to really think about this social norms and moral norms and ethical norms and see whether how we can better teach that to machines such that it really represents diverse set of people's norms, not just Western biased norms. And yeah, that's a huge challenge, but super exciting challenge. I think it's actually opportunity at the same time. And it's important to draw in experts outside computer science for that. I'm really realizing that this is such a big issue. AI people cannot solve on their own.
Yeah, thank you. I mean, that's it's somebody with a social science background. I certainly resonate, with that. But I'm constantly amazed at the many different perspectives that different people bring. I want to use that as a lead into thinking about how we can democratize the creation and use of AI. I mean, right now the scale and compute costs of building these massive scale models is only possible in a few large organizations. And so my question is, how can we expand access to models to ensure innovation, insights that come from a wide range of people across industry, academia, consumers? Yijin, let me begin with you, since you have positions at both, a company, have taken part in the Alexa Prize, a professor at University of Washington. How do you see us opening up some of the capabilities that are right now locked in a small number of organizations?
Yeah, great question. GPU or TPU donation would be the most appreciated. No, I've been begging. By the way, even though I'm part-time at AI2 is nonprofit, so there's no GPU farm in the way all the other tech companies do have. So I've been begging, Google to donate some TPUs. And in the past, when people were not using it as much, it was easier to get them. But these days, I get the impression that other tech companies are paying for them. So that's part of the big challenge. But, when companies do share their code and or APIs, it helps a lot, because even if it's just the APIs, if we can measure the behavior, and if we can do this at scale, then it can also enable really exciting new capabilities. So actually, since we talked about Atomic earlier, we had this new Atomic 10x distilled from GPT-3, which is for the first time better than what humans have authored. It's not the case that GPT-3 is actually having that level of a common sense just yet. So it's that plus algorithmic approach that we named as symbolic knowledge distillation. And so after some filtering, very aggressive filtering and additional work, we found a recipe in which large-scale, high-quality knowledge distillation is possible. And then that sort of gave us a bit of this realization that, this is like proof of concept for potential possibility, even offer from smaller models like GPT-2. So we have a new work that we're going to archive this month sometime, in which instead of relying on GPT-3, now we use GPT-2 to generate high-quality, large-scale, diverse knowledge, and it's actually better than GPT-3. So algorithm can do a lot, but the availability of API helps so much when the model itself is too large to share. And by the way, since we're talking about it, so I also appreciate OPT being publicly available. And my first reaction was, well, what am I going to do with it? I cannot fit into my GPU. But I would like to give a bit of a credit to this 16 to 8-bit compression work. It's due to my colleague Luke Zellmoyer and amazing co-authors, including Tim Detmer's PhD students at UW. And that suddenly enables a lot of people to be able to host a very large model in their relatively, shabby GPUs. So that also helps a lot, that sort of research where people compress without any loss of performance.
You also talked about the Atomic 10x, where one of the things you described was using symbolic knowledge distillation. So it's a very different level of abstraction, and that in and of itself may be broadly useful instead of just going sort of undifferentiated, flat associations.
Yeah. Yeah.
So I think there's a lot of innovation that comes from that. Eric, can you talk a little bit about the Turing academic program and maybe some of your recent work on, Codex and CodePilot for code generation? Because both of those share APIs a little bit more broadly.
Yeah, one of my comments is if we really believe the prospect that Yejin and I mentioned earlier, that there will be surprises and important work on the scale parts of the problem. We need to, of course, pursue all sorts of ways to compress and distill and work with smaller models when it comes to resource constraints. But it is interesting, we're in a world now where only a single handful of computing facilities in the world can build the largest models. And working with a colleague, we just put down back of an envelope, constructing and maintaining even a big single model. Some of these named models we talk about can be as costly as building the Large Hadron Collider. And what does that mean for the community? And so we're concerned, and Microsoft leadership is concerned about the sharing and the democratization of these technologies and tools, and want to go beyond just fine-tuning opportunities in compute, but like actually giving full access to models and the ability to compute new ones. But as a start, we stood up the Turing academic program for sharing out models and providing compute on a request for proposal basis. We've had some really great collaborations and teams working with these tools. One of the concerns was minimizing the risks of abuse of the large scale models, and that's come up as possibilities at the same time as promoting their availability. Now, I'd say more broadly, this is a national and international concern with academic access to resources, compute and infrastructure to build these large scale models and to work with them. When I was working as a commissioner on the National Security Commission on AI, the NSCAI, last year, we put a lot of effort into thinking about what might be done in terms of the kinds of national, for the United States at least, and European and other countries, what kind of new kinds of investments do countries need to make in AI? And some of the work that we were working on in this report led to the National AI Research Resource Discussions in a task force that's come with a report due out soon. But I think it's going to take federal investment, NSF involvement, the new NSF directorate, private-public partnerships. We've been talking to NSF about how we can help to move forward on this. Of course, breakthrough ideas with lighter weight going from GPT X to GPT-2 and showing you can get far. These going from 16 to 8 bits and so on. I mean, these are great ideas, but I'm not sure that they're going to hold up in the long term to give academic colleagues the same resources that industry provides their research teams and developers.
Yes, Eric, in describing the many ways that we can more democratize the creation and use of these foundational models, you mentioned some really important issues about responsible innovation. How can we, as designers and developers, ensure the models we build, especially in settings like healthcare, finance, places that are just touching the core fabric of people's lives, how can we ensure that those models are fair, transparent, controllable, used ethically? Can you share some of your experiences in co-founding the Partnership on AI as well as Microsoft's Ether program?
Yeah, it's interesting that the work in this space, for me personally, was interested in AI facing the complexity of the open world technically, and that led into considerations of influences on people and society more broadly. So the opportunities are deep. It's so interesting how far we've come with computing generally, but AI in particular, in terms of going from a boutique kind of world of possibility where just getting something to run was fabulous. You look at it in an office and we celebrate it was running, to where these systems can really have significant influences in influencing people's lives and decision-making that affects populations. So this led me and others, colleagues, to form the Partnership on AI, a nonprofit that brought together all the major companies with civil society representation, as well as nonprofits, to work through sets of issues that we laid out as being areas or pillars of where we see thinking, reflection, technical development, as well as regulation and policy being important. Now, simultaneously, we set up a board at Microsoft, or an effort called ETHER, which stands for AI Effects in Ethics in Engineering and Research, working with the senior leadership of Microsoft 6 years ago. It's coming on, and coming on 3 years ago, we set up the Office of Responsible AI, a compliance team. These teams work together. Let me just say that as part of the ETHER work, which involves research, some of the best researchers at Microsoft working with product team partners on issues like fairness, error analysis, notions of interpretability and transparency, have led to a bunch of innovations and developments. But for me, it's been more about what's a model of responsibility for corporations. I'm also interested in for governments and for academic groups. On our side at Microsoft, one of the most interesting aspects of ETHER was setting up a sensitive uses review program. And to date, we've reviewed almost 500 cases which come in through a certain set of criteria of being a sensitive use of AI, where we think through and come up with policies and programs. We also have a process, I just realized I didn't ask you a question about Copilot earlier. We have a process that we look at, we set up specially, we call it LASER, for longer term AI safety in engineering and research, for looking at emergent properties or capabilities, either through the core foundations of the technology emerging or a new application like Copilot, where we're all of a sudden generating code. To look through and make recommendations. With Copilot, for example, that effort led to over 50 recommendations that we asked the product team to make before Copilot shipped as general availability. And you can imagine concerns. Could Copilot, which generates code recommendations, be used to insert security vulnerabilities into code secretly? Could Copilot be used to amplify the ability to generate malware and so on? We had to think through what were the interesting issues moving forward.
Thank you, Ye-Chin. I know you've also thought a fair amount about, malevolent uses, adversarial uses of some of these technologies, especially in the context of generative language models. So any additional thoughts to add?
Generative models are very powerful, but also that's where all the hidden gems that are really horrible come out of control super easily. And I think that really motivates. One benefit of that is that I think it really motivates the community to really think about the problems in, partly in the human society that led to such a data that is biased and riddled with all the problems. So I think partly we do need to really think about how to address all these biases and toxicity in a systematic way, both from to reduce that from the data, but also from the model that is already trained on, because I don't think it's actually just as simple as, find a better data. There's no such a better data.
Right.
All the data reflects the problems that humans have, and it's very bad when machine amplify it. So I think we really need a community effort in order to address it. I do not believe it's possible to just rely on regulations such that do not allow deployment of any of the generative models. That's not going to happen. I think some people believe a bit too much on just relying on regulations. I do believe the regulations are really important, and that part of the world needs to catch up to meet the desired level of AI deployment. But however, I think we also need to address it from inside, from the AI research and models.
Yeah, I think you've both highlighted how much we as computing professionals need to take responsibility for these things. And although there are lots of challenges, we are almost at that time. Let me just ask each of you in 30 seconds to reflect on your greatest hope for the future of AI over the next 5 or 10 years. Eric?
Well, first of all, I believe we're going to make great progress on addressing these concerns with fairness, security, privacy, rough edges, disinformation, toxic output. It's going to take some technical policy work on industry, civil society, and government. My aspirations, it's been so exciting to be an AI researcher since the mid-'80s and watching these waves and helping to contribute to waves of innovation. I'm completely and continue to be mystified about human intelligence. I started with neurobiology and moved into computation. I'm hoping to really gain more fundamental understandings of computational intelligence and how it relates to human cognition. On the AI side, I'm really going to push and hope we'll see great work on complementing human intellect and abilities moving forward with AI systems. I see tremendous upsides in the realms of creativity, invention, artistry, visual arts, music, design. I think we'll see great work in education, assisting with learning. In the sciences, methods that supercharge scientists' abilities, as well as helping with discoveries in chemistry and physics and biosciences. There'll be significant advances, I'm sure, in medicine, climate, sustainability, directly attributed to AI advances.
Okay, thank you. Ye-Jin, you have the last voice here on your greatest hope for the future of AI development.
Wow, yeah. I hope that we can finally crack common sense, knowledge, and reasoning. I mean, we did make a lot of progress, but we're not there yet, and that would be super exciting. And I do hope that those findings will be also helpful for better representing social norms and moral norms, and really make a system that can potentially help address the problems of the society, speaking such a biased language or biased representation of people that caused that bias in the AI in the first place. And I do hope that we can have a positive AI that can make positive impact in the society.
Okay. With that, I think we are at the end of our time for the Fireside Chat. I want to thank everyone online for listening, and especially Ye-Jin and Eric for sharing your amazing insights about such a broad range of really, really important topics, and help us think about what's next in large-scale AI. Thank you.
Thank you, Sue. It's been a great discussion.
Thank you so much.
Thank you for joining us today to share our research progress on deep learning and large-scale AI. I hope you have enjoyed listening to my Microsoft colleagues and external collaborators as they share their thoughts about existing and emerging research directions. At Microsoft Research, we aim at building AI that benefits more people more often. With this goal in mind, we approach AI from many different perspectives, ranging from understanding how large AI models work at their fundamental levels to developing new and emerging applications of AI, while taking into consideration privacy, fairness, trust, and other key factors for creating more responsible and inclusive AI. In today's track, we focused on 3 emerging research directions, namely efficiency, adaptability, and human-AI collaboration. Efficiency gains will bring in many benefits, ranging from making real-world usage of recent AI advances more affordable, and hence bringing their benefits to more scenarios and more people, to reducing their environmental impact. Research that makes AI run more efficiently in computing hardware by using less processor time, less memory, and so on, can reduce both the operational and embodied emissions associated with AI-based tasks. We heard about exciting work on running AI on the edge and optimization libraries like DeepSpeed that makes distributed training easy, efficient, and effective. We also discussed how we can optimize existing models with model compression techniques that combine pruning and neural architecture search to identify the best student architecture, and knowledge distillation to transfer knowledge from the larger teacher to a smaller student. We are very excited about the recent progress in exploring new sparse model architectures, where we can scale up the model size without significantly increasing its training and serving cost. We are also exploring more modular model architectures, so that instead of only building bigger monolithic AI models that are expensive to train and serve, we can make AI models more modular and specialized, while jointly optimizing model structure and model parameters. Such models will not only be more efficient to train and serve, but also easier to adapt to new tasks. Adaptability will be a very important factor for the next generation of AI models. AI today only covers a small number of the skills compared to humans. To bring the benefits of AI to a broader set of scenarios, we need to develop AI that can learn to quickly accomplish new tasks. Most AI models are developed using learning methods that assume that the world is static and that the data for all of the tasks that the AI model needs to perform will be presented to the model for training. You heard from my colleagues and collaborators in session 3 today discussing several research directions where we can improve generalization to new unseen tasks and also improve robustness to changes in distributions and operating environments. Many high-stake real-world settings, such as automation and healthcare, require AI models to be able to generalize well to situations that they have not seen before. The performance of current state-of-the-art AI models can significantly regress due to such changes. We believe training models that can quickly acquire new skills without compromising already learned skills is critical for bringing AI benefits to the next level. We are already seeing that continual learning paradigms and modular designs that encourage combining different specialized modules can improve generalization and adaptability, especially in multitask settings. Human intelligence has a remarkable ability to quickly adapt to new tasks and environments. Humans can acquire new skills and learn how to solve new tasks by imitating the behavior of others or by following natural language instructions. We believe we need to develop interactive, collaborative agents that can naturally interact in a dynamic multimodal environment and learn to perform new tasks from arbitrary human instructions. This paradigm of experience-grounded learning would combine reinforcement learning and supervised learning, allowing AI agents to learn quickly and adapt as they interact with changing environments. I'm very excited about the work we heard about in the fourth session today toward developing, deploying, and evaluating interactive multimodal agents in a Minecraft-based environment. We chose to study this problem in a Minecraft-based environment to enable researchers to focus on advancing new learning paradigms while avoiding the inherent complexity of deploying an agent in the physical world. We're also excited about collaborating with many colleagues across multiple institutes to develop and share this work with the broader community through competitions like IGLO and MineRL Basalt in Europe. Thank you again for joining us today. If you like to learn more about these research areas or are interested in opportunities at Microsoft Research, please do not hesitate to contact myself and my Microsoft colleagues. Thank you.
That's a wrap for day 1 of Microsoft Research Summit. I hope you've enjoyed this day of presentations and discussions among researchers at Microsoft and our many colleagues and collaborators from around the world. We'll reconvene tomorrow for a plenary session on the foundational work we're doing to power the next generation of the cloud, followed by another full day of exciting tracks and sessions. See you then.